Quick revision video on covalent bonding, and be sure to subscribe for new content. So we'll start with the essentials. Covalent bonding occurs between non-metals, and we find covalent bonding in non-metallic elements, so for example hydrogen, chlorine, compounds of non-metallic elements, so things like carbon dioxide, water, glucose, and polyatomic ions. So these are ions where you've got more than one atom bonded together in the ion. So hydroxide ions is a covalent bond between the O and the H, and the sulfur and these four oxygens, you've got covalent bonds as well. In most cases, covalent bonding leads to the production of simple molecules. So these and these are all simple molecules, as are sulfur dioxide, hydrogen peroxide, and ethanoic acid. However, in a small number of cases, covalent bonding leads to the formation of giant covalent structures, and the examples we need to know about are boron, carbon, and silicon. And finally, the covalent bond is defined as being the electrostatic attraction between a shared pair of electrons and the nuclei of bonded atoms. So moving on to dot and cross diagrams now. So these are the diagrams we use to represent simple covalent molecules. So if you want to pause the video and have a go at those first. So fluorine, two fluorine atoms covalently bonded. So I've got these, apologies for the quality of the diagrams, I'll just quickly scribble these down. So each fluorine atom obviously has 7 outer electrons. So I've got 7 pink crosses and 7 blue circles, and you can see there's the covalent bond. That's that shared pair of electrons. So these negatively charged electrons are being attracted to the positive nucleus of that fluorine atom and that fluorine atom, and that's what's holding the thing together. So moving on to water, so there's its dot and cross diagram. So you can see there are 6 oxygen electrons, the blue circles, and we've got single covalent bonds between the 2 hydrogens. And the other thing to note on there is these electron pairs here that aren't involved in bonding, they're called lone pairs. Ammonia next, so there it is there. So nitrogen has 5 outer electrons, so we've got 3 single covalent bonds to these 3 hydrogens, and we've got another lone pair here. And methane, CH4, looks like that. Got 2 more examples to show you. These are slightly unusual, so you'll see why when you see the dot and cross diagram. So BF3, boron trifluoride, there's the dot and cross diagram there. So the unusual thing about that is there are only 6 electrons around the outer shell of boron, the valence shell. So that's actually still stable because boron has formed the maximum number of bonds it can. So boron, because it's only got these 3 outer electrons, is stable once it's formed 3 covalent bonds. Again, these are single covalent bonds, just one shared pair of electrons. SF6, or sulfur hexafluoride, the unusual thing about this now is we've got more than 8 electrons in this valence shell. We've actually got 12. So why is that possible? Sulfur can, it's called, expand its octet, so it can go beyond 8. And that's because it has available orbitals to accommodate more electrons. So moving on to multiple covalent bonds now. So these are bonds that involve the sharing of more than one pair of electrons between the bonded atoms. So far we've only dealt with single covalent bonds. So in other words, on this slide we're looking at things like double bonds and triple bonds. So if you want to have a go at those 4 and then play on when you're ready for the answers. So oxygen first, we've got a double covalent bond between the 2 oxygen atoms. So you can see to make it work, so in other words have 8 electrons in the outer shell of each atom, we've got to put 2 electrons each into the overlap, the shared part. So each atom is sharing 2 electrons, hence that's a double covalent bond. Carbon dioxide, you've got 2 double covalent bonds, so between the carbons and the oxygens. Nitrogen, you've actually got a triple covalent bond there because each nitrogen is sharing 3 of its valence electrons. And hydrogen cyanide, HCN, we've actually got a single covalent bond between a hydrogen and a carbon, but we've got a triple covalent bond between the carbon and the nitrogen. So we're finishing with dative covalent or coordinate bonds. Both terms mean the same thing, and what it is, it's still a shared pair of electrons between the atoms, but one atom is supplying the pair of electrons. So far we've seen both of the bonded atoms contributing electrons to the shared pair or the shared multiple pairs, whereas now it's just a single atom that's providing the electrons for the shared pair. Just going to look at one example here. So it's the ammonium ion, that's NH4 1+ charge. So this ammonium ion is actually made from an ammonia molecule and a hydrogen ion. You'll notice the H+ ion has no electrons. So what's going to happen? Well, the lone pair of the nitrogen in the ammonia molecule can provide a pair of electrons for this bond here. So it's still a shared pair of electrons, but both of the electrons have been supplied by the nitrogen atom. So this here is a dative or coordinate bond. Obviously the charge is maintained, so the whole thing now gets wrapped in a square bracket with the positive charge outside. And another way to represent this, we haven't really used this representation at all yet, but you could represent this like that, and you'll notice here that the arrow here is showing the dative covalent bond or coordinate bond, and the arrow direction is showing from where the electron pair originates. So the electron pair is originating from the nitrogen, and it's gone to this H that was the H+ ion, and so you can see the arrow is going from the nitrogen to that hydrogen there.